Welcome to Wicked Sick Shit with no physics. I had to leave out the shit because, well, actually, I couldn't put the things. I'm used to the list host, and you give me trouble whenever I try to send explicit things. But anyways, this talk is about one of the more awesome aspects of going into space, and that's the explosion that gets you there. And so I'm going to be talking about what is really just a variety of ways to make explosions. And some explosions will be slower than others. Sometimes you need a slow explosion. But you're probably wondering, why do we want explosions?
I mean, it's one of those questions I rarely have to ask.
So the fact of the matter is, we haven't gone to the stars yet. And this is a problem. The closest we've ever gone is with the Voyager space probe launched in the 70s. And they basically went out to about 100 astronomical units, and they're still going. But at the rate they're going at, it's going to take a while. They're only going about 1/10,000th of the speed of light, And if they were heading towards the closest star, Proxima Centauri, it would take them about 72,000 years to get there. But since they're obviously not heading towards Proxima Centauri, it's going to take them eons and eons, right? So this is a bit of, there's some engineering involved. You want to go to the stars, you need to make a spaceship that goes faster. But before we do that, we're going to have to discuss some principles. Oh yeah, and ignore the science here. This is engineering. Okay, so this is our stellar neighborhood, and we'll just discuss a few destinations we just might want to go to. So the sun's here. Alpha Centauri is about 61 degrees below the ecliptic of the solar system. It's about 4 light years away. Bernard star is about 6 light years away. And we originally thought that would be a great place to go because we thought there were exoplanets there. But the evidence for that is no longer so substantial. And Sirius is another close one, as well as Tau Ceti. And all these are within about 12 light years or so. So the question is, can we do better? Can we do better than the Voyager spacecraft? And the question is, the answer to this is the most definite yes. But the principle behind this essentially is we have to consider a factor that is often considered when we're talking about propulsion systems, and this is called specific impulse. And it's basically the amount of momentum change you're going to get per kilogram of propellant you carry. And because the unit is pretty much like dealt with mainly by engineers, it's got really wacky units, and it's got a really nonsensical thing factored in it. So basically, the engineers say it's basically the change in momentum per unit weight of propellant, and weight being the weight you measure at sea level. So when you take so basically there's like a G factor in there, and so what you get basically is the unit actually ends up being seconds because momentum is kilogram mass times velocity. So, and you have to divide it by the G, the acceleration at sea level. So you end up getting seconds. But if it's but most scientists and people that know what they're doing say use they end up just taking they actually do it per unit mass, so it ends up just being in units of velocity. So let's see. As a gauge, so some common specific impulses. Chemical rockets have very, very low specific impulses. They only have 450 seconds. And the reason that this is so important is because you have to remember that you have to accelerate the mass that you carry for fuel. So you want to carry as little fuel as possible. So you need to make sure that you're getting as much momentum per bit of fuel that you're carrying. So rockets have very poor specific impulse, but they have very high thrust. And obviously turbofans are very, very good specific impulse, but they don't work outside of the atmosphere. And their thrust isn't so good. And we'll ignore some of this stuff. And so here's a graph. I'm going a little fast because I actually have 2 talks in one. So yes. So for comparison, rockets have very poor specific impulses. Ramjets have better and better. The best ones are turbofans. but we can't use turbofans because they operate in space. All right. So, propulsion systems with very high specific impulses. This means we need to liberate lots of energy. So let's go back. Let's go even farther back because there is an equation support. So an equation you can derive to gauge the performance of your rocket. This is actually important here. This is the non-relativistic Tsiolkovsky rocket equation, which means that the amount of your final velocity for your rocket is equal to the velocity of the exhaust in the reference frame of the rocket times the natural log of m naught over mf, where mf is the fuel, the rocket's fuel. So m naught is the dry mass of the rocket after it's burned all its fuel. Mf is the fully fueled version of the rocket. For those of you who want a derivation of this, just go to Wikipedia, and there's a very quick one. I'm not going to do it here. So the velocity of the exhaust. So first of all, the velocity of the exhaust is actually a direct. So the velocity of the exhaust is going to be dependent on the specific impulse, because that's the stuff when you end up converting everything. So if you have ISP equals the delta P over if you have that delta P over per kilogram equals the mass of the exhaust. So let's say you burn a kilogram of propellant. This is going to be directly proportional, basically, to the this is going to be directly proportional to the exhaust velocity. So this is going to go directly, like linearly proportional. This is going to have a direct linear effect on the actual final velocity you can get for your rocket. And then there's a factor in like the natural log too. But anyways, so basically that's why it's important to have a specific impulse if you want to directly relate that to the rocket equation. Okay, so here's some very high specific impulse things. The first thing we're going to talk about was invented by a man named Stanislav Ulam. He was a very crafty fellow. If you've ever looked at, well, basically the design for the thermonuclear weapons that we use today is directly based, well, it's his baby basically, him and Teller. They basically, so the whole idea of using a fission warhead, like a nuclear weapon, to channel radiation down, and the radiation pressure ends up causing the conditions that allow fusion to happen, were all Ulam's like brainchild. He also had some contributions, Monte Carlo integration, which is a numerical technique to do things. But the point I'm trying to make here is he had a very accomplished intellect and a very accomplished life. But all these things paled, in his eyes, to one particular idea he had. And he would often proclaim that this was his proudest invention. And this invention that I will mention is nuclear impulse propulsion. And so the three projects I'll be talking about that have to do with this are Project Orion, Medusa, and the Project Longstone. And if you're still wondering what this is, okay. It's basically, so essentially what nuclear impulse propulsion, we're going to go down. The idea came about in the 40s. It was the late 40s, and I believe the Castle Bravo shot, which was the Castle Bravo thermonuclear blast was performed. The thermonuclear test was performed. Okay, and what happened is, if you were to look closely here, you'd see that about 30 meters away from ground zero, there are two spheres made of metal and coated in graphite. And what's so special about the spheres is they're not going to be destroyed. Instead, they're going to be shot several hundred meters, and all the graphite is going to be ablated and blasted off. But the spheres are going to be intact. So engineers and scientists thought, okay, well, this is promising. We've got this very powerful bomb. Why don't we use this to propel a spaceship? So, I'm going back. Okay, so the first ideas to actually accomplish this were come up with by so Lockheed Martin, you know, is the conglomeration of Lockheed Martin. Back then, the precursors to this was the Martin Company. They were just Martin. They hadn't merged with Lockheed yet. Their idea, they thought, let's make a rocket powered by nuclear bombs. We're going to make a combustion chamber that's 130 feet in diameter. We're going to shoot water into it. We're going to set the bomb up. It'll vaporize the water, and then we can shoot the hot steam out the back. You know, This is